Okay, so let's talk about Newton's universal law of gravitation. This describes the mass, or the force, the attractive force between two objects of mass. I want you to know what the formula is. I rarely ask people to actually calculate this force, but I do want you to know the relationships between the gravitational force between objects of mass and the variables that we'll see. And so this is given by these forces between two masses. It's given by, we'll call this F12, a constant. This is the gravitational constant. You know what, I'm not even going to give you the number because it doesn't even really matter that much. Because I'll never ask you to actually calculate that. Times the mass of the first object times the mass of the second object divided by the distance between them squared. I'm going to call this R12. It's just the distance between the two objects squared. I want you to notice that F12 here is equal to F21. That is, the magnitudes of these vectors are equal. They are actually equal but opposite, or equal and opposite. They're equal in magnitude, but they're opposite in direction. A couple of relationships here I want you to recognize. One is that the force, the gravitational force, is proportional to the mass. So, if the mass goes up, for example, then the force will go up by the same amount. So if I double the mass, I double the force. And that sort of makes sense, right? That if I'm standing here on the surface of the Earth, there is a force between me and the Earth, about 700 newtons or so. But if I double my mass, then that'll be a bigger force. I'll have a bigger weight by the same amount. If I double my mass, then I'll double the force. Similarly, if I increase the distance between the two objects of mass, then the force will decrease by a lot more because it's an inverse square relationship. That is that F is proportional to 1 over R squared. So for example, if R doubles, then F is going to go down by a factor of 1/4. We'll see that in a clicker question soon. Where if I change one of those variables, the mass or the radius, or excuse me, the distance between the two objects, r, then that'll change the force in these various ways. We've had questions like that before, but you'll see them again. So in Newtonian physics, forces are instantaneous. However, let's see, all the forces we've had have had some means of transferring them. And in particular, we're talking about contact forces, right? Like when Nelson Zamora whacks you in the face, the contact is between his fist and your face. It's a contact force. That is the types of forces that we've been talking about. But field forces, on the other hand, they are transferred in some other way that we don't fully understand. We're beginning to understand it, but they are transferred in some other way. And so there's a lot of questions about this. Do they require some time to transfer? And how are those field forces transferred? And it is thought that they do require some amount of time to transfer. It travels basically at the speed of light. So that, for example, if you were to take the sun out of the solar system, if you could just remove the sun instantaneously without any mass at all there, then the planets would continue orbiting around that sun at least for a few minutes until that force, the amount of time that it takes to transfer, that time has elapsed. And there is an observatory called Ligo. Has anybody ever been to Ligo? Yeah, I've been too. Isn't it awesome? Yeah, I forget your name. Emma? Yeah, so y'all should really go to Ligo. They won the Nobel Prize last year. Or was it last year? I think it was last year. They won the Nobel Prize for detecting gravitational waves. And they've done it once or twice since then as well. They, by the way, they have Science Saturdays. I think it's once a month. And so you can look on their website, just Google Ligo Livingston, which is where it is. It's in Livingston Parish. And you can go up and visit Ligo on these Saturdays. They have really great activities for adults and kids too, by the way. and you can actually take a tour of their operating room, for the operators of the observatory, and you can see some of their instruments. It's a really cool. Do you have a good time on the tour, Emma? It's definitely worth going, and they won the Nobel Prize for that work. I have a short video that I'm going to show you, but first let me just show you in short. No, go back. I'm going to draw a little figure, and we'll stay on this page. Draw a little figure about what LIGO is, and then I'll show you this video that describes it in a little more detail. I want you to know what LIGO is, and in short what it does. It detects gravitational waves. LIGO is called an interferometer, and an interferometer has two arms that look like this. And at the end of either arm, there are mirrors. We're going to get into interferometers next semester when we do light, but just in short, they send a laser down one side, and then it reflects back, and then they send a laser down another side. It's actually the same color, but I'm going to draw it different colors, and it comes back, and these two lasers combine here, and they produce what we call interference. When two light waves come together, they interfere with one another. Again, we'll talk about interference next time. No need to write that down. We'll talk about it next semester, rather. But these two light waves interfere in a way that is proportional to the length of these arms. And these arms on the interferometer at LIGO, they're very long. They're about 4,000 meters long, about 4 kilometers. And it's thought that when these gravitational waves come through space, when they travel through space, they make space get shorter or longer, shorter or longer. And so what LIGO has been looking for is for these arms to get longer or shorter, longer or shorter. And then they use the interferometer to actually measure that distance very accurately. Now, it's not very much that it gets longer or shorter, a fraction of the diameter of an atom, perhaps, but it's still something that they've been able to measure. Let's watch this video. They describe... All right, it really is kind of a big deal. I hope that it instills some sense of awe in you that though we've known about gravity for hundreds of years, or thousands of years even, but we've known about it as scientists for hundreds of years, that there's still some mystery in how it operates, and that as we go into this millennium, that we're continuing to learn more and more about how gravity works. So for this, I want you to be responsible just for knowing what LIGO is. It's this interferometer used to detect gravitational waves. You need to know what it stands for. It's the Large Interferometric Gravitational Observatory, and then also that these forces are transferred by gravitational waves in some way. All right, so we've already talked about weight. It's the force due to gravity. Let me just put it here that our force weight is equal to our mass times the acceleration due to gravity. So for example, an object that has a mass of 10 kilograms, it will have a force weight equal to 10 kilograms times 10 meters per second squared. Notice that I didn't put a negative sign here, and that's equal to 100 newtons. The reason I didn't put a negative sign here is because I always draw my vector downward, and so that negative is encapsulated when I draw my vector in the negative direction. So whenever you're calculating weight, you just use a positive g, the 10 meters per second squared. But then we'll always draw our vector towards the Earth, which is where the force weight is acting towards. From Newton's law of gravitation, it's pretty simple to derive the acceleration due to gravity. So I'm going to show you that here. I'm not going to ask you to calculate that acceleration due to gravity, but again, I might ask you to explore some of the relationships between the variables, between A, R, and M. Newton's universal law of gravitation, G, M, that's M1, M2 over R squared. But we also know that the weight of an object is equal to M times G. We know this observationally or from Newton's second law. We can take these two and put them together, and we get GMM over R squared. Actually, I'm going to make one of these a big M and one of them a little m. So like the big M would be the mass of the Earth, and the little m would be the mass of the person or whatever the object is. And then this is going to equal to M times G. So here my masses cancel out, and then I get this nice expression for the acceleration due to gravity. It's another way that we can measure this, gm over r squared. We can measure what is the acceleration due to gravity. And it's dependent upon a couple of things. It's dependent upon the mass of the Earth, or whatever planet you happen to be on, if the mass of that planet is smaller, then it'll have less gravitational acceleration. And then it's also dependent upon the radius of that planet, or whatever object you're on. That's the distance from the center of mass of the planet and the surface. So here, G is proportional to M, and G is proportional to 1 over R squared. So just like we had with Newton's universal law of gravitation, if I increase M, I increase G by the same amount. If I increase R, I decrease G by that amount squared. So if I double this is a factor of a quarter. Just put that in there for example, and we'll see some questions like this in a bit. So if I double this, then I would quarter my acceleration due to gravity. You can measure the mass of the Earth very accurately, and that's what the GRACE mission has been doing for the past, decade or a couple decades, I think. The NASA GRACE mission, this is a NASA satellite. It's actually a couple of twin satellites, and the way it works is, you have the Earth right here, and then you have this satellite that's going over it. And in the satellite, there's it's just a pendulum really, that goes back and forth, just like y'all did in a lab, right? Y'all in the lab, I think it was the second lab, you measured the period of the pendulum, and then by measuring the period of the pendulum, you were able to calculate what is G. So you measure the period of the pendulum, and the period of that pendulum is proportional to the acceleration due to gravity. So that satellite, all it has is a pendulum inside of it. It's not quite the same as what y'all use. It's a little bit fancier, but not much. It's a pendulum, they measure the period, and then they can calculate what is the mass of the Earth. Why would they want to know the mass of the Earth? Or more particularly, why would they want to know the mass of the Earth at this particular point? Like not the mass of the entire Earth, but just the mass of the Earth underneath that satellite. Why would they want to know the mass of the Earth? Can you think of a reason? Or next, I guess, we would consider is, does the mass of the Earth remain constant? It doesn't remain constant, at least not the localized mass of the Earth, because you got all sorts of things moving around on the surface and underneath the Earth. You got water tables that are moving around, and that's mainly what GRACE is doing, is they're looking for water and how it exists and moves around on the Earth. They can measure currents in the ocean. They can measure currents at the bottom of the ocean with this by analyzing the acceleration due to gravity. They can find water tables that were previously unknown. They can measure how water tables are increasing or decreasing water supplies for people in cities and all around the world. And so it's a really nice mission to measure the mass of the Earth and determine how fluids move within the Earth. That's the NASA GRACE mission. We might watch a video about it in just a bit, but let's move on for now. We'll come back to it. Okay, so the acceleration due to gravity on Earth is 10 meters per second squared. We've already said that. It is different on other planets, though. On the Sun, with the acceleration due to Earth, the acceleration due to gravity would be bigger or smaller than what it is on Earth. What do y'all think? It is bigger, in fact. But actually, on the Sun, you have a couple of things going on. The mass goes up, but then also the radius goes up as well. So as the mass goes up, that causes the acceleration due to gravity to go up. But as the radius goes up, that causes the acceleration due to gravity to go down. But the net effect is that the acceleration due to gravity is bigger. On the Moon, is it bigger or smaller than the Earth? It's smaller, definitely. In fact, it's more obvious with the Moon because the Moon is more like the Earth. It's a rocky planet, or it's a rocky moon. And so it's smaller because the mass is smaller. On Mars, it's also smaller than the Earth. But how can a body with less mass than the Earth have a greater acceleration due to gravity? What's a way that a body, a celestial body, that has less mass than the Earth, how could it have a greater acceleration due to gravity? If it had a really small radius, right, so if it was really dense. So if you have a body with a very small radius compared to the Earth, it will have a bigger acceleration. All right. Let's see. We're going to skip this part about the moon. We're just going to calculate g, but we'll skip that. All right. So we had Newton's first law. Newton's first law was the law of inertia. Newton's second law was the law of what? You recall? It's the law of acceleration. And now we're looking at Newton's third law. Newton's third law is sometimes called the law of reaction or action-reaction. We've already seen it with regards to the universal law of gravitation, because if we have two objects of mass, one mass is big, one mass is small, they're still going to exert exactly the same force on one another. And so that's a nice manifestation of Newton's third law, which says that if I have one force, I have to have an equal and opposite force that accompanies that. So here, in words, if objects 1 and 2 interact, the force F12 exerted by object 1 on object 2 is equal in magnitude but opposite in direction. To the force F21. And we've already seen that. Like I said, with Newton's universal law, we have one force in that direction, and we have another force that's equal but opposite. F12, F21. A similar thing is true if I push on a surface, then I'm going to push with a certain force. The surface will push back with exactly the same force. So let's say, for example, that I have an object that's just sitting here on the ground. Let's say that this object has a mass of 5 kilograms. And so what is the force, the gravitational force, that's acting downward on this object? What is the magnitude of the gravitational force that's acting downward on that 5 kilogram mass? 5 kilograms times what? Times 10 meters per second squared. Right, so my force weight here is 5 kilograms times 10 meters per second squared. And that's equal to 50 newtons. But Newton's third law says that if I have two objects interacting, in this case, this is the block pushing onto the floor, then the floor has to be pushing back on that block. And it has to be pushing back with a force that is equal but opposite. So the floor is going to push back with a force that's exactly equal to 50 newtons. We're going to begin calling this the normal force. We'll see it in a bit, but this is called the normal force. And we'll have to know how to calculate that normal force in a variety of scenarios, including the inclined plane. The result of this law, which seems sort of funky for a bit, but is that no isolated force exists. That you cannot have one force without having another force. That if you have one force, you'll always have another force that's a reaction of that. And as I said, this is called the law of reaction or action-reaction. Because it sort of pairs these forces into an action force and then a reaction force. Like, for example, here we would call this our action force, and then the responsive force is the reaction force. All right, let's see, I want to show you one other video this morning. I'm going to stop